Hello everyone, welcome back to the channel. In this particular video, we are going to discuss AAHL paper 3 first question, and it is November 2022 series, right? So let's go with that. It is mixed one, so it's a highly investigated kind of question. So yeah, let's go through it, and multiple concepts involved from simple like differentiation, proving by mathematical induction, a lot of things included here. So I'm going to break it up and make it simple for you. Let's get into this. Right. So this is a question basically. We are going to work on the series, and this particular series is sigma I is equal to 1 to n I power q. Right. And so when you expand it, we know, right? When you substitute I equal to 1, it's 1 power q and then summation, right? So plus the next 2 power q plus 3 power q and so on. We're going to proceed this till n power q. And n q both are positive integers, 0 is not included. And okay, there are so many sub questions. First one and the first set of questions are very simple. When q is equal to 1, the above summation, sigma notation, this series will become arithmetic. So in this case, I need to prove this. Let's go. Show that I is equal to 1 to n I. So which means I just put k is equal to 1 here. I need to prove this. Let's start with LHS. Right? We have to start with LHS and we will end up with the RHS value, the terms. So LHS is sigma I is equal to 1 to n. Let me expand it. So when you substitute I is equal to 1, it's 1. Then plus next I is equal to 2. So just 2 and 3 and 4 and so on. Finally, it will end with like n minus 1 and n. Right? So this is nothing but sum of all first n odd natural, that is simply natural numbers, right? So that's simple. And it is an arithmetic series because the common difference is same. When you find common difference by any two consecutive terms, it's going to be 1 here. So it's arithmetic as they have mentioned. Okay, so for arithmetic series, what's the formula? There is sum of the terms, which forms an arithmetic series. So sum of series in an arithmetic sequence will be Sn is equal to, we have two different kind of formula. I'm going to use, okay, let me show you both of them. It is available in the formula booklet. And here we go. Here you can see, this is one and this is the another one, but we're going to choose this. When you know the first and last term, this can be implied. Okay, so this is what we're going to do. And let's take this. Both can be done. This will make, and we can save the time when we go with the second one. Let's switch into the solution page. Here we go. So we have chosen the formula from the booklet. And here, Sn is equal to n by 2 u1 plus un. So what is un? The first term. Un, the last term. Let's substitute. Sn is equal to, and this will go like this. N is n only, so nothing changes here. U1 first term is 1 here, and un is n. So this can be written as 1 by 2 n. N plus 1 plus n can be written like this, so that I can make an exact form what they have given. So this is nothing but RHS. I have started from LHS. Now I have proved the RHS, and hence the proof is over. Very simple, and it carries just 1 mark. Now let's get into the next part. Now the table of values is given when n is 1, 2, 3. This is what n square, and sigma is equal to 1 I power q. So this is the series we are investigating about. And it is also given, we have to find what is p, right? So sigma I is equal to 1 to n iq expansion, we know. It goes like 1 power q, 2 power q, 3 power q, and so on, n power q. This is general. But look, what is my p? When n is equal to 3, what is yours? This summation value is what they are asking for. So replace n is equal to 3. Sigma I is equal to 1 to 3 I power q. This can be expressed as 1 power q. Wait a second. So this can be expressed as okay, actually here there is a change. It's I power 2 sigma I square, not I power q, I square. So this will go like, it's not like complex number I. So this will go like 1 square, 2 square, 3 square, and so on, n square. Right? So sigma I is equal to 1 to 3 I power q. I power 2 means 1 square, 2 square, plus 3 square. And it's very simple. Like 1 plus 4 plus 9, it's going to be 14. This is nothing but my p value. So p is 14. Right? Very simple. And this will fetch us around 1 mark. Right? So next part. Second part in B. Sigma I is equal to 1 to n I square is a1n, a2n square, a3n cube, where a1, a2, a3 are rational numbers, positive rational number. We have to find 3 system of linear equations here. So let's go with each case. And when n is 1, when n is 2, when n is 3. This is what we're going to do. So when n is 1, what happened? Sigma I is equal to 1 to 1 itself. I square is a1. What is my n? My n is 1. So 1, let me use brackets, then a2, 1 square, plus a3, 1 cubed. Okay, and this can be right. What is sigma I is equal to 1 to 1 I square? It's just 1 square, right? 1 square is 1 equal a1 plus a2 plus a3. This is the simplest one we got here. When a is equal to 1, this is what we got. And when n is equal to 2, sigma I is equal to 1 to 2 I square, and this side will become a1 2, a2 2 square, and a3 2 cubed. And this will fetch us, okay, right side, 2a1 plus 4a2 plus 8a3. So just simplify the numericals. And what is sigma I is equal to 2 to 1 I square? So you can do like this. Like 1 when you substitute 1 square plus 2 square, which is 4 plus 1, 5. Otherwise, you can use the table values also. This is what I square, right? The table values also we can go with. So this is my second equation. 3 system of linear equation we need to form here. Let's go. Okay, the last case, when n is 3, what happens? When n is equal to 3, sigma I is equal to 1 to 3 I square equal a1 3 plus a2 3 square plus a3 3 cubed. Okay, what happened to this when I simplify? Sigma I is equal to 1 to 3 I square. So 1 to 3 I square means it's p. We already found it. That's 14. So left side it's 14 equals 3a1 plus 9a2 plus 27a3. We got a third equation too. So that's simple. We construct 3 linear system of linear equations. Right? And next part is to solve this. Hence, find the values of a1, a2, and a3. Right? So we can take these and let's get into the calculator page. Here we go. Okay. So in this, you can go for the calculate and menu. In algebra, we have the solve system of linear equations. We have 3 variables and 3 equations in number 3. It will change to x, y, z. So that A1, A2, A3, we can relate it back. And okay, so in each entry, we are going to give the equations that we have, right? So let me copy the equations now. First one is very simple, A1, A2, A3 equal 1, which is here x plus y plus, sorry, x plus y plus z equals 1. So next equation is 2a1 plus 4a2 plus a3, 8a3. So that is 2x plus 4y plus 8z equals 5. And next one, 3a1, 9a2, 27a3. So which is 3x plus 9y plus 27, sorry, 27z. And it is equal to 14. That's it. We have given all the things and let's go for the solution part. So click enter. We got this, which is x is 1 by 6, y is 1 by 2, z is 1 by 3. So let's take this to the solution page. And we can, and that's it. We got the values of A1, A2, A3. Right? Hence, find the values of A1, A2, A3. And here we go. My A1 is 1 by 6. A2, it's 1 by 2. A3, it's 1 over 3. That's it. We have completed this. And let's get into the next part. Okay. So in the next part, we have right. So moving to the next part. Right. So getting into the next part, consider the function f of x. And in this particular, we're going to investigate. We are going to generalize the thing, whatever the formula we have learned, right? So we have seen we are going to generalize for all values of q, and that is what we're going to do step by step. And consider the function f of x is 1 plus x square plus and so on plus xn, and n belongs to z plus. Show that x into f dash of x is this. Okay. First, let me find f of x. F of x is given to us, f dash of x. This is a very basic x power n rule, right? So if your function is x power n, its derivative is n into x power n minus 1. And it's very simple for a polynomial function. So f dash of x, it's a constant, it will become 0. Okay, and then plus x will become 1. X square will become 2x. And then x cube will be there, right? Let's imagine. Let's take that too. So 3x square and so on. Previously, we will have before x power n, we will have x power n minus 1. That will go n minus 1 x power n minus 2. And here we go n into x power n minus 1. So, right, differentiation is over. Now, f dash of x I have. What I need to prove? X times f dash of x. So, let us multiply by x on both the sides. And that's simple. So, we will have xf dash of x, which is my desired LHS. And right side will become, okay, 0, it will vanish. And x into this thing. 1 plus 2x, 3x square, and so on. N minus 1 x power n minus 2 plus n into x power n minus 1. Okay, let's take the x inside and we will get this. X plus 2x square plus 3x cubed plus and so on. N minus 1 into x power. Already we have n minus 2. Now 1 will join, so n minus 1 plus n into x power n. So the coefficient and the exponent of that term is exactly the same. So this is what we need to prove, and exactly we have done that. LHS, RHS, right? So we got it. F dash of x, f dash of x is this. Right? Very simple proof and with simple differentiation technique. Next, we're gonna observe a family of functions here. F1 of x, like we did x f dash of x, right? This is going to be represented as f1 of x. Then f2 of x is x f1 dash of x. Then f3 of x is x f2 dash of x, and so on. This is the general format. Okay. So let's consider this and we are going to solve the upcoming questions based on this. Now, show that f2 of x is this form. Sigma I is equal to 1 to n I square x power I. Okay, so what is f2 of x actually? When you look at the functions, family of functions, we can see that f2 of x is x f1 dash of x. X f1 dash of x. Okay, so I know x, but what is f1 dash of x? We don't know, right? So let's go with f1 of x. This is what x f dash of x is f1 of x. So let's take f1 of x now. F1 of x is x plus 2x square. This is very easy to memorize. Just 3x cube and so on plus n x power n. Okay, let me differentiate this. F1 dash of x is like a polynomial differentiation. X will become 1, 2 already there, x square will become 2x, 3 already there, x cube will differentiate as 3x square plus and so on plus n. X power n will be differentiated as n into x power n minus 1. Right? So now we have 1 plus 4x plus 9x square plus n square x power n minus 1. This is f1 dash of x. But what I need to prove, f2 of x is x f1 dash of x, right? So let me take x, multiply by x. So x f1 dash of x is x plus 4x square 9x cubed plus n square x power n. Okay. Actually, I have this form, like actually that should be plus and so on, right? I missed it. Let me add it up here. Just note it. Here too. Right. But I need to prove in this structure, sigma notation we have to. It's quite simple. So you can write x is common, like if first term x power 1, second term x power 2. And also I can write this as 1 square, right? X power 1. Then this can be written as 2 square, 1 square x power 1 plus 2 square x power 2 plus 3 square x power 3. Then next one will be 4 square x power 4 and so on, n square x power n, right? So now you can write it as sigma I is equal to 1 to n. Okay, which is changing here? Here 1, 2, 3. The base of the coefficients are changing. The exponent of the power variables are changing. So that I can give I. So I power 2 is fixed and then x is fixed. Power is changing, that is I. So x f1 dash of x is equal to this. And we have proved this. You can just relate it. Exactly, we have that. Okay, x f1 dash of x is nothing but f2 of x as per the given family of functions. So this could be the better and best answer. One extra step. Just making sure like this. Okay. So that's simple. And we can get into the next part. Right. Now prove by mathematical induction f q of x is equal to sigma I is equal to 1 to n I power q x power I, where q belongs to z plus. So the same thing what we have proved is for f2 of x. Now we have to generalize this, right? We proved for f1 of x, we proved for 2. Now we are going to generalize, and this is particularly using mathematical induction. So let's get started. The three-way method, right? We have three rules over here. Let's go. Okay, first we have to make a statement. Let me make the statement as PQ. This will help us in much way, like whenever we want to write the statement, we can save time. So PQ is FQ of X can be written as sigma I is equal to 1 to n I power Q x power I for all Q belongs to Z plus. Okay, this is what we have taken. Now, first case is what? When for the very first values, we are dealing with Z plus. So my first case is when Q is 1, not 0, right? When Q is 1, we have to prove it. Let's try to prove F1 of X is equal to, and I will derive. What is F1 of X? Let's go and revisit the family of functions here. F1 of X is nothing but this. We already have it. X, F dash of X. I can show you here. F1 of X is, this is what they have given. And X F dash of X, we already have it. Like the fancy form. 1x, 2x squared, 3x cubed, and so on. So we already have it. We just gonna take it. F1 of X is X plus 2x squared, 3x cubed, and so on, plus n x power n. This is my Fn of X. And this can be written like this. This is what the proof is. We have to prove for the case 1. And let us take, X can be taken outside. Let me take it out. And I will have 1 plus 2x plus 3x square plus and so on, n x power . Okay, I think we can keep it over here. Okay, so this can be written as 1, 2, 3, 4, 2, 3, and so on, n, right? So this, let me write, okay, I have to express it x power I power q. So x power 1, wait a moment. This can be written as x power 1 times 1 power 1 can be written as 1 power 1. Then this x power 2 power 1. Why I'm writing 1, 1? We are dealing with the case q is equal to 1, right? Plus and so on, x power n power 1, right? So let me take it out. So this can be written as sigma I is equal to 1 to n. And where it is changing, the power of x is changing. So it's x power I we can give. And what about this? It is just I power q. And in the case q is equal to 1. So 1 power 1, 2 power 1. Q is fixed here. And the number is changing. So changing one, you can give I power q. Where here q is 1. So we can just mention just I. That's it. So f1 of x can be written in this way. And we start with f1 of x. We prove the right-hand side of the hypothesis we have taken. Right? And that's simple. Next part. Okay. The theorem is hence proved P of P1 is true. For first trial. For example, the dominoes effect, right? When the first domino falls, then only the sequence will happen, right? So we have proved the first case. And now somewhere some domino will should fall down, right? So that something is can be taken as K. I'm assuming that, okay, somewhere some domino fell down means the next will fall. And eventually it will hold for everything. Now the general case, and this is an assumption. We're not gonna prove it. We're gonna assume and take this for our proof. So assume that PK is true. What is PK? We know Pn, just replace it with K. That is true, we have taken. We didn't prove it, we just take it as it's proven one, like we're gonna use it. So Pk of x is equal to, so is nothing but the Fk of x is equal to sigma I is equal to 1 to n. Here we have I power q, x power I. Instead of q, I have taken k. So I power k, x power I. So we have taken as true. So this pk is true. So we can use this in our further proving parts. Right? I hope this might be clear here. Right. And moving for the next part, when k is equal to 1, whenever like 100th domino is falling, it should hit the next. So if it hits the next, okay, it's completely the domino effect is great, right? So when the case q is equal to k plus 1, what is up? I assumed kth domino fall. Now we are taking for the k plus 1th domino, right? What happened here? We need to prove it. We can use the previous, whichever I have used to start. So when q is equal to k plus 1, what we need to prove? To prove fk plus 1 of x is equal to sigma I is equal to 1 to n I power k plus 1 into x power I. So let's go. Right. So let me take the left side, fk plus 1, and we can derive the right side. So LHS is equal to fk plus 1 of x. Okay, we're going to revisit the family of functions. And this is what? Actually, fq of x can be written as x times fq minus 1 dash of x. This is what generally the family of functions is conveying to us. So now I can write this fk1 of x can be written as, so we are going to use it. And this is x times f k plus 1 minus 1 of x. So which is x fk of x. Got it? Right. And next part. Okay, LHS we have started x into fk of x. Let's go with fk of x. We already defined, it's not proven, but we have assumed it. So fk of x, we can directly take it. Fk of x, let me use different color. Fk of x is equal to sigma I is equal to 1. We assumed fk of s is true, so we can apply it. I power k, x power I. Okay, let's expand this, and it will go like I power 1, which is I power 1, x power 1. Sorry, 1 power k, x power 1 power k, x power 1, then 2 power k, x power 2, then 3 power k, x power 3, plus and so on, plus. When I'm dealing with n, it's n power k, x power n. This is what my fk of x. Right. And we are going to do, okay, here dash will come. Right. So I want fk dash of x. Let's differentiate. 1 power k is a constant, it's just 1, and x when you differentiate, it's 1. Plus 2 power k is a constant. When you differentiate it, it's 2 power, sorry, just 2x. Then 3 power k is a constant, and x power 3, when you differentiate, it's 3x square. Likewise, and so on. N power k is a constant, and it will be n into x power n minus 1. Right. And simplifying it further, it's just 1 plus 2 power k. Here a 2 power 1, they are in product. So when the bases are same, we have to add the exponent. So 2 power k plus 1 x plus 3 power k plus 1 x square plus and so on plus n power k plus 1 x power n minus 1. This is my fk dash of x. Okay, let me use this over here. What I have LHS and this I'm going to combine here. So LHS is equal to, I got this x into, I don't only know, this is just fk dash of x. So I'm going to multiply x into 1 plus 2 power k plus 1x plus 3 power k plus 1x square plus and so on plus n power k plus 1 x power n minus 1. Now let's take x inside, and this will become x plus 2 power k plus 1 x square, 3 power k plus 1 x cubed plus and so on n power k plus 1 x power n. Can you see? The coefficients base and the variables exponent, they are getting matched. So this is what we have proved it earlier, and it is holding for k plus 1 also. So how I can write this? So this can be written as 1 power k plus 1. So sigma I is equal to 1 to n, 1, 2, 3, and so on n. The bases are changing. So that can be kept it as I power k plus 1 into x, and the powers are changing. X power I. So what I have started with LHS and I end up with RHS. Fk plus 1 of x is this. And this is just pk plus 1 is true. And we can go with the conclusion part. How to conclude this? Since pk is true for n is equal to 1 and pk is true for, sorry, it's pq. pq is true for n is equal to k plus 1 also we have proved. This one we have proved, this one we have proved. But the second one, k plus 1 is proved with the help of whenever n is equal to k is true. So by principle of mathematical induction, I am writing PMI. PQ is true for all Q belongs to Z plus. That's it. We have proved the thing by principle of mathematical induction. Now, next part is very simple one. Okay, so we have to use the sigma notation, and we have to mention that FQ of 1 in sigma notation. So that's the third part. Use sigma notation for FQ of 1. Okay, so FQ of x is proved 1, right? FQ of x is sigma I is equal to 1 to n x power I power q. And FQ of 1 is going to be sigma I is equal to 1 to n 1 power I into I power q, which is nothing but sigma I is equal to 1 to n I power q. This completes this. Right. And let's go for the next part. Now, E part. Consider f of x is this as a geometric series for x not equal 1. Show that f of x is equal to this. And geometric series formula is also given to us. Let me show the formula booklet. Sum of n terms of geometric series is this. Two ways, r power n minus 1 by r minus 1 and or 1 minus r power n by this. So we're going to take this particular and let's use it over here. Let's switch to the here. So what is my u1 here? This is what my u1 is. It is just 1. u1 is equal to 1. Okay, from here the geometric sequence starts. So let it be 1 and we can start with x. So this is my u1 x. And what is the common ratio? That is also x. And n is n only. So let's go. F of x is equal to u1 x into r is x power n minus 1 by r minus 1. I have left that 1, right? Let us write it over here. Let's simplify it. Take x inside. It will go x power n plus 1 minus x by r minus 1 plus 1. And let's multiply this over here. X power n plus 1 minus x plus r minus 1 by r minus 1. Okay, what is my r? It is x. That will be better. So now minus x plus x cancelled. X power n plus 1 minus 1 by x minus 1. This is what we need to prove and we have that proof. Right? So that's simple. And next part. For x not equal to 1, show that f1 of x is this. Okay, what is f1 of x? We can relate it with family of function. f1 of x is x f dash of x. Right? And we have that too. Let's switch over there. So this is my f of x. F of x we have just proved. This can be written as x power n plus 1 minus 1 by x minus 1. So for f1 of x, I need to differentiate f of x and then multiply with x. Right? This is from the previous problem. And f dash of x is going to be u dash v, that method. Let me write it over here. The numerator is taken as u, x power n plus 1 minus 1. And denominator is v, x minus 1. Now u dash is n plus 1 into x power n plus 1 minus 1 and minus 1 will become 0. So n plus 1 and x power n. And v dash is just 1. Very simple. Now f dash of x is going to be, let's start from here. F dash of x is u dash v minus v dash u by v square. We know everything, so let's directly substitute. U dash is n plus 1 x power n. U dash. And then v is x minus 1. Minus v dash. V dash is 1. U is x power n plus 1 minus 1. Divided by v square, which is x minus 1 the whole square. And let's go. Okay, n plus 1. Let me take the x power n inside. X power n plus 1 minus n plus 1 into x power n. Then take the minus 1 inside. Minus x power n plus 1 plus 1 divided by x minus 1 the whole square. This is f dash of x. We are solving for f1 of x, right? f1 of x is nothing but x times f dash of x. So let's multiply x. And it will, so when you multiply x on both the sides, here an x will get multiplied x, x, x. So n plus 1, x power n plus 2 minus n plus 1, x power n plus 1 minus x power n plus 2 here. And here just an x. And the denominator remains the same here. X minus 1 the whole square. Okay. So still we can refine this like x power n plus 2 is common. Let me try to simplify. X power n plus 2, take it common, n plus 1 here and here a minus 1 as a coefficient. Then other stuff, let it be remain as it is by x minus 1 the whole square. Okay, so plus 1 minus 1 will get cancelled and we got n into x power n plus 2 minus n plus 1 into x power n plus 1 plus x and whole divided by x minus 1 the whole square. Okay, I think we have simplified as much as possible and this is the result we have to prove. N into x power n plus 2 minus n plus 1 x power n plus 1 plus x by x minus 1 the whole square. Right. And next part, G. Show that limit x tends to 1 f of x is an indeterminate form. It's quite simple. We just now formed the f1 of x in this particular form, right? So let's take this. Okay. And we're going to apply limit x tends to 1 on both the sides. Limit x tends to 1. Limit x tends to 1. So how will you do? We will substitute, right? Let's check. So n into 1 power n plus 2 minus n plus 1 into 1 power n plus 1 plus 1 by 1 minus 1 the whole square. So n into 1 power anything is just 1. So n minus, this is also 1. But when you take a minus inside, you should be careful. Minus n minus 1 plus 1 by 0 square. N minus n cancel. So I got a 0 by 0 form, which is indeterminate form. And hence we have proved it. Just a 1 mark. This is indeterminate, right? Now, if there is an indeterminate form, we will solve it by using L'Hopital's rule. And yeah, let's prove this. Limit x tends to 1, f1 of x is this one using L'Hopital's. What is L'Hopital's rule? We will differentiate numerator and denominator as much as time whenever we got indeterminate form. When there is an acceptable form, we will stop over there. So limit x tends to 1. Limit x tends to 1 for the whole thing. First, let me differentiate numerator and denominator. Limit x tends to 1. N is there. And x power n plus 2, when you differentiate, n plus 2 into x power n plus 2 minus 1. So it will go n plus 1 minus n plus 1 is already there. And we will bring that for while differentiating whole square x power n plus 1 divided by denominator also you should differentiate 2 into x minus 1. Right? So now let us substitute and check quickly. Okay, this is okay, but 1 power n into, let's do here, n into n plus 2 minus n plus 1 the whole square plus 1 by 2 into 1 minus 1. Okay, anyways, this is 0, but let's check the numerator. N square plus 2n minus, when you expand it, n square plus 2n plus 1 plus 1 and n square plus 2n, take the minus inside. This will become 0. So 0 by 0, again indeterminate form. So redo L'Hopital rule. Okay. Right. So again, limit x tends to 1. When I start differentiating this, n into n plus 2 will stay there. And x power n plus 1 will go n plus 1 into x power n. Then minus n plus 1 the whole square into n x power n minus 1. And this will become 0. This will become 2x. Sorry, just 2. Right? Okay. Now we can substitute and check. Because second differentiation also we did for numerator and denominator. And I will get n into n plus 2 into n plus 1. 1 power n minus n into n plus 2 the whole square into 1 power n minus 1 divided by 2. Hopefully, I think we won't get indeterminate form here. Even if the numerator is 0, right? It's going to be 0. And 1 power anything, it's 1. And I can take n and n plus 2 common. N and n plus 2. take it outside, we will have n plus 1 minus n minus 2. And also 2 we can take common. So n into n plus 2 by 2. Here when you simplify, it's a minus 1. Okay, let's check this. N into x power okay, here n plus 1. Okay, actually here n plus 1 should come. Let's change this. Right. So let's do by, okay, we got this, right? Limit extends to 1. This after first differentiation, let's substitute 1 over here. N into n plus 2 into 1 power n plus 1 minus n plus 1 the whole square 1 power n plus 1 by 2 into 1 minus 1. So this is n into n plus 1, n plus 2, sorry, minus n plus 1 the whole square plus 1 by denominator 0, right? And let's do take n inside, n square plus 2n minus, when you expand it, you will get n square minus 2n minus 1 plus 1 by 0. And everything in the numerator will get cancelled. We got a 0 by 0, which is indeterminate again. So let's reapply the L'Hopital's rule for this function. Let's take this. This is the first differentiation and it doesn't work. So we can redo. Here we go. Right, let's read second differentiation. Again, we are applying the limit. Limit extends to 1. N into n plus 2, that's fine. And n plus 1 will get multiplied inside. X power n plus 1 minus 1 is x power n. Minus n plus 1 the whole square, n into x power n minus 1, and plus 1 will become 0. Divided by 2. Hopefully this time, I think we won't get the indeterminate form. Let's move ahead. So this is limit extends to 1. Okay, we can directly substitute, right? No need to further move on. So let's substitute n into n plus 2 into n plus 1. 1 power n minus n plus 1 the whole square. 1 into n into, right? So n into 1 power n minus 1. And 1 power anything, it's going to be 1. And let's simplify. Denominator is 2. Hopefully we don't have indeterminate form again. Okay, so n into n plus 2 into n plus 1 minus n into n plus 1 the whole square by 2. Let's take what we can take common from the numerator, n and n plus 1. Take it out. And I will have n plus 2 in the first part. In second part, a minus of n plus 1 divided by 2. And you will get half into n plus 1. What happened to this? Here, the bracketing will become 1. N plus 2 minus n minus 1. And minus n cancel. 2 minus 1 is 1. I don't need to mention it. Yes, we have proved this. This is what we need to prove. We start from LHS and we end up with the RHS. Right? By applying L'Hopital's rule, we have proved it. And that's simple. They have break down the concept. It's an investigate-based question. And you can practice it after the video, similar problems like this. And that's it. This will fetch us a total of 28 marks. Completely we can get if we go with the correct process like this. Right? And thank you so much for listening. Let's meet in the next video.